we shall demonstrate proof by mathematical induction for the third time. Example 2.28, applying mathematical induction. Show that for any positive integer n that is greater than or equal to 4, 2 raised to n is less than or equal to n factorial. So a theorem need not always begin with 1, okay, or with n equal to 1. This one begins or is true when n is greater than or equal to 4. Or at least that is what the theorem is saying. Can you still remember the meaning of n factorial? That is how you read it. Lucky for you, you had statistics way back in junior high school and today senior high school. But in my days, we never had stat in high school, which is why I was kind of surprised to see this symbol n factorial. I don't see this. I never saw this in my math subjects when I was in high school. So that is the meaning of n factorial. It's 1 times 2 times 3, so on and so forth until times n. This is the structure of a proof by mathematical induction. You state the theorem, you treat it like a proposition or a conjecture that needs to be proven. Okay, so you have 3 parts to your proof: the base case, the inductive hypothesis, and then you will make a conclusion. So again, you begin by stating the proposition. Let n be greater than or equal to 4. N is a positive integer. 2 raised to n is less than or equal to n factorial. That is the proposition. We are going to prove it. So how do you begin? We begin by the base case. The base case is, you know what, you will show that it is true for the first value of n, for n is equal to 4. So when n is 4, 2 raised to 4 is 16. And 4 factorial is 1 times 2 times 3 times 4. That is 24. And so 16 is less than or equal to 24. So 2 raised to 4 is less than or equal to 4 factorial. So when n is equal to 4, the proposition is true. How about when n is equal to 5? What is 2 raised to 5? It's 32. What is 5 factorial? 5 factorial is 24 times 5, that's 120. And 32 is less than or equal to 120. So this is true. 2 raised to 5 is less than or equal to 5 factorial. We are done with the base case. We shall now proceed with laying down our inductive hypothesis. So it's like we are going to make a tentative assumption that the proposition is true for any positive integer k. This one is equivalent to your set of positive integers. And be sure to change your dummy variable. In our original proposition, we were using n, but in the inductive hypothesis, you must choose or you must use a different dummy variable. It can be k, it can be j. For any positive integer k that is greater than or equal to 4, 2 is less than or equal to k plus 1. Of course, this is true because k begins with 4. What else? From the multiplicative property of inequalities, so pay attention to this. Okay, look at this. 2 to the k is less than or equal to k factorial. That is from our inductive hypothesis. Now, 2 is less than or equal to k plus 1. So, from the multiplicative property of inequality, these two terms are positive, by the way. From the multiplicative property of inequality, you multiply 2 to 2 raised to k, and k plus 1, you multiply it to k factorial. The inequality stays the same. 2 raised to k times 2 is less than or equal to k factorial times the quantity k plus 1. That is just the multiplicative property of inequality, and that is because 2 and k plus 1, they are both positive. You cannot make the same conclusion if 2 and k plus 1 can be negative. Okay, but this statement is equivalent to this. Applying laws of exponents, this is 2 raised to k plus 1. Look at that. And k factorial k factorial times k plus 1 is in fact equal to the quantity k plus 1 factorial. So take a look at this. When we assume that the proposition is true for k, it also implies that the proposition is true for the next integer, which is k plus 1. And that is what we are aiming to do. So from the principle of mathematical induction, or using the principle of mathematical induction, for any positive integer n that is greater than or equal to 4, 2 raised to n is less than or equal to n factorial. And you know what? I forgot to end my earlier proof with this. This notation means your proof is done. You are done with your proof.